Example 6, we have a string instrument now. There's a bridge right here, and someone is plucking this string, and this string is vibrating into a standing wave. Now, we're told that the musical instrument is 60 centimeters long, so this is the length of the total string, 60 centimeters, and the mass of that length of string is 2.00 grams. And the string sounds a A4 note, or 440 hertz, so the frequency is 440 hertz when it's played. We would like to know where must the player slide their finger along here so that a certain distance x from the bridge, all right, so that they could form a D note instead. So right now, with no finger contact for this entire length of 60 centimeters, it's producing a 440 hertz note. Now, we'd like to produce a second frequency. I guess we'll call that F1, and then or F, and then F prime maybe, in 587 hertz. Both of these are really fundamental frequencies. We're assuming that it's just really one single loop. All right, and then B part is without returning. Is it possible to play this G4 note, 392 hertz, on this string? So, what do we need to do? Well, we're given the length and the mass of the string because we need to know how fast this wave is traveling at. Remember that the speed, this was earlier in the previous chapter, chapter 16, is equal to the square root of the tension divided by the mass per unit length. Now, the tension, is that given? No, it's not really given, but we are given the mass. Well, I suppose I could figure out the wavelength, because I really know that this is really just one entire wave here fitting in. And I know that is 60 centimeters. So let's just put this to the side, come back to it in a minute here. We know that L must be equal to, well, that's half of a wave. So half of lambda in here. And we know L is 60 centimeters. So the wavelength of the string wave would be twice this length, which is twice 60 centimeters. So this wavelength is 120 centimeters, or I suppose we could say 1.2 meters. Now, if we know the wavelength and we happen to know the frequency, we could figure out the velocity that way. Frequency times wavelength. So we'll take that first frequency and that wavelength in that oscillation mode. So the frequency is 440 hertz, and the wavelength lambda is 1.2 meters. So that means that our speed is 528 meters per second. Okay, now we would like to change our length, so essentially x. We have to get a new wavelength, right? And a new distance, x, so that we can produce it. Now, you have to think, what is not changing in this scenario? Well, the speed. Why? Because you still have the same mass per length. You're playing the same string. And the tension, you're not tightening this over here, I assume. So the tension's remaining the same. So the speed is remaining constant. So what you're doing is you're changing the frequency, you're increasing that frequency, and then hence you're decreasing the wavelength, which is going to affect the distance L, or in this case x. So using the speed of 528, we're going to use F prime times lambda prime for this new frequency of 587 hertz. So the new wavelength for that particular frequency would be the speed divided by the frequency we want to achieve. So 528 meters per second divided by a 587 hertz note. And this will give us a wavelength of 0.899 meters. It's not our answer yet, because remember, we're only fitting in half of a wave. So our x distance is going to be half of that wavelength. So 0.899 meters divided by 2, which is about 0.45 meters, or 45 centimeters. So that's part A. What about part B? We'd like to return to a note that is 392 hertz. We want to return to a note that is a lower frequency than this, like F double primed of 392 hertz. How's that? How can we do that? Well, think about it. If you are going to go to a lower frequency, that means you're going to need a longer wavelength. You're going to need a longer wavelength to fit in to this distance. But the thing is that the bridge to the fingerboard here, or this distance right here, where they're attached here, you can't go any further than that. So there's no way you could produce that note. You don't have enough distance. You can't go beyond L. Essentially, X primed, I guess, will be larger than L, which is basically impossible. Okay, so you can produce notes with higher frequencies because you'll require shorter wavelengths, and you could fit them into there and move your finger down here. But you can't produce lower frequencies because you just can't simply slide your finger further on. You can't make that string any longer than it actually is. Okay, hopefully that makes sense to you. And that's it for example 6.